example, the DLL of the VML. Okay, there are a lot of different versions of the DLL of, for example, VML. It's named VGX, and it's really hard because the code changes between the versions and the code moves around because every time the compiler changes stuff and they compile a new version and they add code or remove code, it always goes up or down. And there is no room for the extra code that you want to add, the code that actually fix the vulnerability. And there's another problem that MS hot patching, which is a good thing, we can't use it anytime we want because it's not there always. If you have an old version of Windows, it doesn't exist there. And there is another problem, which is the Windows file protection. You can't overwrite important files like DLLs or system files, things like that. So we have a few alternatives here that I sat down and thought and used some help with the guys from my team. And we have to remember that we don't want to change the file as much as possible because every change can lead to another bug or failure of the application. So the first alternative we have is patching the executable itself by adding a new section or by finding some room in an existing section and put our code there. So there are a few problems with this alternative because it's really hard to do such a thing in the short time you have. It's not like I can sit down and develop it weeks before I know there is a 0-day coming out. And it's a big change for the executable file and time consuming. I said it's really hard to program such a thing, but in a long and in a short time. And per version patching, it's very popular. If you see EI patch or iDefense and companies like that, you have, or actually they have all the DLLs files and they check each one of them and they do a spatial patch per version. So the problem here is that if you don't have all the versions of the DLL in advance, you're screwed. So another patching alternative is the hot patch. We said already that we have 7 bytes. Maybe some of you recognize the CCs and move EDI, EDI. So the problem with this approach is that it's not good for static or in-disk patching. And the other problem is that you have to patch all the callers and not the vulnerable function because probably it's str copy or mem copy and things like that that can't be patched easily. So you have to patch a few of the callers and then you need more signatures and it becomes harder. So there is spot patching, or I don't know what's the professional word term for this, but this is what I came up with. And it's simple. It means that you search for something that you know in advance how it looks like, and all you do is replace it with a different code that probably should be with our fix, the Z fix. The only problem with this approach is that it doesn't always have the same signature matched for all the versions you want, or either way it's generic. If you have a good signature, you will find all the places you need to patch. Okay, so now I'm going to talk about the VML patching, and I will show some steps that I did in order to find the vulnerable code and how to fix it. So a bit of a background about VML. VML is vector markup language. It lets you describe how to draw, how to draw graphic stuff on the screen. And it was proposed by MS in 1998. The problem was that it was rejected, but Microsoft still insisted to use it, and that's the outcome, indirectly, that we have this 0-day or add. Anyways, this is some of the things you can draw with the VML, and you have 3D stuff even, and grow shading, and crazy things. It's really nice. But one day, in September 2006, someone found, okay, Adam Thomas, a researcher from Sunbelt, found this 0 day. Okay, so the exploitation actually downloads a Trojan and runs some code, show pop-ups and adwares and things we don't like, and this is the good case. The worst case is like stealing your login credentials for your bank and stealing your money, stuff like that. Okay, so now I'm going to talk about the vulnerability itself. So actually it's just a stack-based buffer overflow, and there is a fill method that's the fill of, if you have a rectangle and you want to fill it with some color, then there is a buffer overflow, and the affected file is VGX DLL. Now, if we use the PDB files from Microsoft, we know the exact function, and soon enough I will show you how I did it. But the vulnerable systems are Internet Explorer, and I mark it specially with asterisk because it's not true. We will later get to this point again. And even the XPSP2 is also vulnerable to this 0 day. So actually just surf and get pwned, and you're screwed. So I ask myself, what if DEP is enabled? DEP is data execution protection, and it's a way to prevent from buffer overflows to get executed and to get pwned actually, but technically way. So there is hardware enforced DEP and software enforced. It doesn't really matter. DEP can be bypassed with read to lib and things like that, but actually it will mitigate most of the attacks if the DEP was default on for Internet Explorer. The problem is that it's not. So the HTML exploitation of the VML is pretty straightforward. We can see here the fill method with the long buffer, which will eventually buffer overflow the stack buffer, and you get some code. There is this behavior line you see here with behavior URL default VML. This is the line that actually loads the VGX DLL that has this fill method function called with the argument. And so this is another thing I came up with and call it vulnerability point. It's actually the instruction or the function itself that has the vulnerability, or that overwrites the stack in this case. So what I did is taking the old code of the HTML exploitation, put a big buffer there, and this is what happens immediately. And notice that this DLL is not verified for some reason, I don't know. So now we know this DLL is the VGX DLL, and we can continue from there. And this is what we do. And what happens next is that we raise an access violation because there is a pointer on the local stack that tries to write somewhere not in memory, so we get an access violation. So now that we have this access violation, we can see the faulting address of the instruction and start analyze from this point. So the parser tokenizer, probably, nobody really knows the official name of this function, is ptoke. That's what I showed earlier with the PDB symbol. And this ptoke actually is a C++ function, and the reason I say so is because there is this move edx, ECX plus VML null terminated string input. So this is where it gets the string from the HTML code and puts it in the edx register. And later on, we can see that edx is the index that counts over the string, and it takes words. This means it's Unicode or UTF-16, and it copies it to the buffer in the member of the class, of the instance, of course, because, again, ECX is used, it means in Visual C, at least, that it is a C++ code. So what we have next, is this line, move edi dx. Dx was already copied here with the input you supplied, and now it overrides the stack. So this is the vulnerability point. The reason we want to know about the VP, in short, vulnerability point, so is that we can now determine where we want to patch it. And it can be in the caller or the function itself. We will see soon. So this is a code analysis of a friend from the team. His name is Michael Hailey. And what we can see is the W char is Y char. It's the Unicode, and the ptoke doesn't get any arguments. And it's a class, of course, but by the name tokens. Again, the symbol from before. It's about the name. And we can see here the actual buffer that gets overflowed. So notice there is the n size and IDX input. We will talk about it later. Okay, so this is the C++ translation of the code, and what we can see here, if you have, okay, so we can see here actually that it's like str token of the C library, and the problem is that there is no check against the size of the destination buffer. So you can see that the end size here is the size of the input we supplied. Okay, so it doesn't really matter. It's copies until the end of your buffer, not the destination buffer. So what the Zert patch actually does is a simple thing as this. To check the end size, this is, again, the input size of our string, and to return if it's too large or above 256 bytes. So I ask myself, why does Microsoft write this ptoke rather than using str token? Okay, so we can see that ptoke is C++, and it has its local storage, which is an improvement for the str token one, and it supports multiple concurrent reads if we think about threads and stuff like that. So str token can be used only once per thread, and in this case, it doesn't change the original string. That I'm not sure why they needed it, but this is the way it works. So if we actually give it a string in Zert with Rust, for example, or do we, its result in the next strings returned every call is in Zert with Rust. Every time we call this ptoke, this is what we get. So actually, if it was used by str tokenizer, then the input was nullified. So we have the in, and then it's a null character, and then Zert again, a null again, and the input string is destroyed or touched. Maybe they didn't want it. Oh. So we talked about threads. So now that we know that the vulnerability point and the function that allocates on the stack the buffer, and we want to patch it. So eventually we need a way to find where to patch the file. Okay, whether if it's in memory or if it's on disk, we need to patch it and find something that will tell us this is the place, this is where you have to change the code and fix it. So for example, we need a sequence of a few bytes probably. It can be short, long, it doesn't really matter, but the point I'm trying to say is that if we use a mask like wildcards, if we have this GIF87A or GIF89, then it becomes GIF8 asterisk wildcard, whatever comes in, and A. So yes, it also can be GIF now 85 that doesn't, that is not wanted, but you get the point. So because there is a mask, we can miss the, actually no, again. We use the mask in order to find the same code in different DLLs.